So let's go to the slide. Recall from not that long ago, our last PowerPoint discussion, that a C% confidence interval, right, for any particular confidence level C, for an unknown population mean, when the population standard deviation is known, right, we need to know it 'cause it's part of our formula, is, right, our best guess, which is the sample mean, plus or minus our margin of error. Our margin of error is that critical value Z sub C times sigma over the square root of n. Now, let's contemplate for a second. What about this formula is unrealistic for actually using this in real life? Right? What about this cannot actually be utilized if you were to try to really use this as, say, an applied researcher or an applied statistician? Exactly. What the cutta? It's unrealistic. It's unrealistic that we would actually know the population standard deviation without knowledge of the population, right? Our formula has sigma in there, and in reality, right, we probably would not know sigma if we didn't know, right, the entirety of the population. But if we had knowledge of the entirety of the population, that would mean that we know the population mean, in which case there is no point to gathering a sample and computing a sample mean and getting a best guess for something we already know. Do we see that inconsistency? The whole point of doing a confidence interval is we don't know the population mean. We want to come up with a range of values, a plausible range of values for what it might be. Agreed? But if we don't know that, how can we possibly know what sigma, the population standard deviation, is? Turns out, in reality, we almost never do. So how do we solve this in practice? Well, in practice, Chapter 2 comes to the rescue, right? Just like we use x bar as our best guess for mu, we can use S, the sample standard deviation, is our best guess for sigma. That is, we do not know the population standard deviation sigma, so we replace it with the sample standard deviation S. That's our best guess, right? We look at the sort of inherent randomness or variability in our sample, and we use that as the best guess for the inherent randomness and variability in our population. Now, I wish it was that simple, but unfortunately doing this, unfortunately using S instead of sigma, right, it changes the underlying mathematics of our confidence interval. And the end of the day punchline is that we now need to generate our critical value in a different way, right? It changes the critical value. Our critical value is no longer calculated under the assumption that the sample mean follows a normal distribution, which is essentially what we did before, but rather it's calculated assuming the sample mean follows something slightly different, called a T-distribution. So a T-distribution is another type of continuous random variable that we're getting a very brief exposure to. The T-distribution looks a lot like the Z-distribution. It's symmetric around 0. That means it's centered at 0. Half its area is to the right of 0, half its area is to the left of 0, right? That's symmetric to Z, right? Z, remember, is a normal distribution with a mean of 0 and a standard deviation of 1. It's bell-shaped, just like a Z distribution. It's named after a letter of the alphabet, right? And T rhymes with Z. Lots of similarities. If you were to draw one next to the other, the human eye probably could not discern the difference. But the difference is that a T-distribution has what's called fatter, it's not a flattering word, fatter tails than a normal distribution. That is, a T-distribution has a little bit more area, a little bit more probability off in the tails than a normal distribution would. Now remember how a normal distribution, its width, right, was ultimately controlled by its standard deviation? Well, a T-distribution's shape, and when I'm talking about shape mainly I'm talking about its width, how compact it is or spread out it is controlled by a quantity known as its degrees of freedom. So degrees of freedom is a somewhat technical term Mathematically, it refers to like ranks of design matrices, which is something mathematically well beyond the prerequisites of this course. Just think of it as a number, like the standard deviation that controls the shape. Now, when making confidence intervals and using a t-distribution to come up with a critical value, the degrees of freedom that we use are always our sample size minus 1. So, our new and improved formula, more realistic and more readily applied to real life, for a C% confidence interval for an unknown population mean mu when the population standard deviation is unknown, is still centered at our best guess, which is the sample mean, still plus or minus a margin of error. It's just that margin of error is tweaked a little bit. We replace the unknown sigma with the sample standard deviation. Mathematically, that changes how we calculate the critical value. It's now based off a t-distribution rather than a z-distribution, and that t-distribution has n minus 1 degrees of freedom. Now, finding the critical values, finding that t sub c, it's not particularly difficult. You have to use a table to do it, although I guess you could actually. There's some ways of doing it in the calculator. Our book walks us through how to use the table and perhaps walks us through how to use the calculator. However, we could get the entire interval, not just the critical value, by using our TI-8384 calculator. And by doing that, sort of cut out the middleman. By doing that, we don't need to find the specific critical value. So how do we do this? Well, again, we go to the stat menu, right? We hit the stat button. We go to the test menu. I believe it's right below z-interval is something called t-interval. We select that, and then we proceed just like before. We'll have a bunch of fields that we need to fill in, and we fill them in. We put a little cursor over calculate, and we hit enter. Alright, so here's an example. A new Math 121 exam is written. We wish to know whether the mean time, the average time, the true average time it takes for all students to finish the exam. Well, how can we do that? Well, we'd have to have a sample of students take it, and we would have to see how fast on average our sample finished. So let's say that we give it as a sort of test run, a trial run, we give it to 50 students. We record how long it takes each of these 50 students to finish the exam, and it turns out that the average time to completion, the sample mean time to completion, is 53 minutes. Now, in reality, we probably would not know the population standard deviation, so what would we do instead? We would take that information, right, using the formula from Chapter 2. We would take the information in our sample, we would apply that formula to it, and we could find out what the sample standard deviation is. Let's say that it ends up being 7. So, right, I go stats, I go over to test because it's useful on a test, I pick a t-interval, and then you can see the screen where I filled in all the information. The sample means 53, right? Notice, when I pick t-interval, the calculator does not ask me for sigma because it knows. It knows that if I'm using a t-interval, I'm using the sample standard deviation. Pretty smart for a calculator. The sample standard deviation is 7, the sample size is 50, we're asked, right? Look right above the printout, right above the screenshot. We're asked to do a 95% confidence interval, so I fill in 0.95. I select calculate, and here's the actual interval. The actual interval goes from 51.011 to 54.989. So, the interpretation would be what? The interpretation would be that we are 95% confident that the true mean time to completion for this test is between 51.011 minutes and 54.989 minutes. Could we come up with a meaningful conclusion? Could we come up with an actionable conclusion based on this confidence interval? Well, I think we could. For example, if this test is being given or intended to be given in a 50-minute class, what would we conclude? We would conclude that although we do not know how long, on average, it takes for students to finish this test, we do know that it's going to range, or we sort of expect it to range, between 51, well, essentially 51 and 55. Small amount of rounding there. That entire range, that entire interval, is more than 50 minutes, right? So I would conclude that if students only have 50 minutes, that this test is probably too long, and some questions, maybe one or two, need to be removed from the test. Yeah, pretty useful, right? And pretty cool. We're finally starting to get to sort of applied real-life uses of statistics. Now, here's a query for us. If we wanted instead a 99% confidence interval, would it end up being larger or smaller than the one we found for 95%? Good. It's going to be larger, just like it was for the z-interval. All those relationships we talked about at the end of the last PowerPoint still hold for the t-interval. I encourage you to actually compute that 99% confidence interval for some extra practice and see for yourself that it is in fact bigger, right? Seeing is believing.